All right, welcome to example 3 from 8.1. Just another system. It's got a little bit of an uglier manipulation at the beginning. We are still doing this graphically. We're going to look at algebraically in 8.2. Because we're doing it graphically, we need to manipulate them to get them into a kind of a friendlier graphical form. So that really just means we need to isolate y, just like the second example that we did there. I think the easiest way is just moving the y, but then we do have to move the 35 as well. I'll write that in 2 steps. So we have 2x squared minus 16x is equal to y minus 35. So then I'm going to add 35 to both sides. So in my calculator, we'll do that in a second here, y1 is going to be 2x squared minus 16x plus 35. And then I'm going to take the other equation and really do the same thing, manipulate and isolate for y. So 2x squared minus 8x minus y is negative 11. I'm going to add the y, and we'll do this one in one step. I'm going to add the 11 at the same time. And I end up with 2x squared minus 8x plus 11 is equal to y, and that's going to be my y2. Now, this is certainly a friendlier way of presenting the systems of equations, especially when we get to doing this algebraically. Isolating y is almost never a bad idea. And if you remember, back in Math 10, you talked about substitution and elimination. That's now actually perfectly set up for elimination. Even though I wrote y1 and y2, they are both the same variable. And the only reason I wrote it as y1 and y2 is because that's how we're going to put them into our calculators. We are doing this graphically, so you do need a calculator. I still have the info from the previous examples, so we're going to clear that. And then we're going to type in our isolated y formulas. So y1 was 2x squared minus 16x plus 35, and y2 was 2x squared minus 8x plus 11. And then again, I like to start on Zoom Standard. We'll see what it looks like. If Zoom Standard doesn't give us the kind of view we need to see the intersections, then we can change our window after the fact. The nice thing about using the calculators is that it is very easy to change the window settings. All right, a lot of students struggle with the fact that, what if these intersect again? There's a lot of in-depth math as to why they don't. The real reason is because these graphs are changing at the same rate because of that 2x squared term. But the bottom line is that you really, really need to be comfortable with tweaking your window settings. So because I'm not sure if maybe this red line is crossing with this blue line somewhere up above, we have to make sure that we're very aware that this is y max, this is y min, x max is on the far right, and x min is on the far left. So I need to increase the value of y max to see more kind of vertically upwards on my scale. So I'm going to make y max, and again, this is just a guess. I'm going to triple it. It's really important that these calculators give us a huge advantage in that you can recreate graphs and tweak graphs without having to spend a lot of time. So you want to be comfortable enough with manipulating and tweaking them so you can get a much better look at the graph. And I think it does show a lot better now that these lines, they're not technically parallel, but they are growing or changing at the same rate. And I think it's reasonable for us to say that they're never going to cross again. Maybe I'll just make that a little bit larger. And it is kind of nice that we can go really kind of overkill. I'm going to make that 300. And when I graph this, we're not going to get, great looking parabolas. It almost looks like they're different graphs, but this is going to show us really, really convincingly, I would argue, that these graphs are only intersecting at one point, right? We can really, I hope, clearly see that this red and blue line is never going to cross again up here, and it's never going to cross again down there. If you still don't believe, continue to increase y max, but they don't cross more than once. To find that intersection, that solution, I'm going to use second, trace, option number 5, which is the intersect, and I'm going to put my cursor directly on there. All right, y1 is the blue graph, that's good. Y2, or the second curve is y2, that's good. And then my guess is pretty much right where it needs to be. And it tells me that my solution is 3 and 5. So x is equal to 3 and y is equal to 5. And it's really important that together, that's the solution. So if I look at this manipulation that I've just done here, this systems of equation has a solution at the point 3, 5. Now, the solution is telling me that if x is equal to 3 and y is equal to 5, these two curves intersect, or they share a value, or that is the solution to that system. To verify this, and I'm going to say this, 20 times probably before we're done chapter 8, you need to use the originals. So although this, black boxed equations are wonderful and they're useful in the calculator, we have to go back to the original forms. So I am going to check if 2 times 3 squared minus 16 times 3 minus 5 is equal to negative 35. That's 2 times 9 minus 48 minus 5 is negative 35. So that's 18 minus 53 is negative 35. And we do get that negative 35 is equal to negative 35. So that's verified. And what some students will do is they'll just check one. And they'll think, okay, 3 comma 5 is on that curve. So I'm good. It's on the line. The problem is that it has to be on both lines. And although it can seem tedious and a lot of work, and do I really need to do this? Yes, you do. That solution, x is equal to 3 and y is equal to 5, has to be a point that's on both curves, so we have to check both equations. To do that, we're just going to substitute the same values of x and y into the second equation in our system. So we are going to check if 2 times 3 squared minus 8 times 3 minus 5 is negative 11. So this is 18 again, minus 24 minus 5 is negative 11. 18 minus 24 is negative 6. Negative 6 minus 5 is negative 11. And again, that is verified. So because this coordinate, 3 comma 5, is on both of those curves, it's the solution to the system. Now, it is valuable, again, I think just to state explicitly that it is the only point that is on both of those curves. And I just want to make that connection one last time with the graph. Looking at this graph, we can see that there is only one point where the blue parabola and the red parabola cross. So there only exists one solution to this quadratic system.